13, 14, 15, we're solving trigonometric equations using more than one function. So we're going to substitute in and try to get them written either in terms of all the same function, or sometimes they have more than one and you end up having to factor them out. Again, you're going to want to have this table handy so that you can go ahead and look up the values once you have your equation solved. You also will need some of your identities. So you'll want to have your sheet with your Pythagorean identities, your double angle identities, all of those different identities that we used before, because we might need to substitute in by using one of our identities. So find your identities if you don't have those sheets handy. The ones with the Pythagorean is probably the most common one that you're going to use, or your double angle ones, depending on what we have here. I think most of these are just using the Pythagorean one. So for our Pythagorean identity, sine squared of x plus cosine squared of x equals 1. Therefore, sine squared of x would equal 1 minus the cosine squared of x, or cosine squared of x equals 1 minus the sine squared of x. Those are the most common ones you're going to substitute in for. You don't always substitute in, but most of the time we're going to try to do that to see if we can get it in terms of the same term. So if I have negative cosine of x minus sine squared of x minus 1, I'm going to have negative cosine of x equals minus, and in for the sine squared of x, I'm going to use 1 minus cosine squared. Then I'm going to simplify that. So negative cosine of x equals negative 1 plus the cosine squared of x minus 1. Solving that so that my cosine squared is positive means I would add my cosine of x. So 0 equals the cosine squared of x plus the cosine of x minus 2. Now I'm going to solve these like the previous ones by factoring. So I'm going to have the cosine of x, that's my cosine squared. The end is negative, so 1 plus and 1 minus. I want a positive in the middle, so I need a plus 2 and a minus 1. So either the cosine of x is going to equal a negative 2, or the cosine of x is going to equal a positive 1 when I move my numbers to the other side, since those are equal to 0. So then I'm going to look them up in my table. So looking for the negative 2. Cosine of x equals negative 2. If I look down my list, there are none for that one. Cosine of x equals 1. At 0, just did 0 and 2 pi. So in this case, I'm just going to have one answer. Again, normally I'd have 0 plus 2k pi, but I don't need the 0 in front. So just 2k pi with k being an element of z. So if k was 0, I'd have 0. If k is 1, I'm going to have 2 pi. If k is 2, I'm going to have 4 pi, and so forth and so on. Number 14. I have 2 sine squared of x minus, or equals 2 minus cosine of x. Again, since this has cosine, I'm going to substitute in there and say 2 times 1 minus the cosine squared of x equals 2 minus the cosine of x. So 2 minus 2 cosine squared of x equals 2 minus the cosine of x. Since I want my cosine squared to be positive, I'm going to move these two things over here. So I'm going to subtract my 2, which happens to cancel that out, and add my 2 cosine squared of x. So 0 equals 2 cosine squared of x minus the cosine of x. Factoring that, I can take out one of my cosines, which leaves me 2 cosine of x minus 1. So either the cosine of x equals 0, or 2 cosine of x equals a positive 1, cosine of x equals positive 1/2 then. So looking up in my table for the cosine equals 0, I am at pi over 2. Cosine equals 0 at 3 pi over 2. Those ones I'm going to be able to combine because they're 90 degrees apart, or not 90, 180 degrees apart. 1/2 pi over 3. Cosine of x equals 1/2 at 5 pi over 3. Those ones I'm not going to be able to combine. They're more than pi apart. And so, putting this into one answer, since I can add pi to get to 3 pi over 2, I'm going to have pi over 2 plus just a k pi, with k being an element of z, or can't combine those ones, and those periods are 2 pi, so pi over 3 plus 2k pi, with k being an element of z, or 5 pi over 3 plus 2k pi, with k being an element of z. And so in this one, whoop, my box didn't draw. Those three things would go in for my answer. All right, number 15. Now you notice we have a different one. We have cotangent squared. Our cotangent squared of x is equal to the cosecant squared of x minus 1. Again, that's one of your Pythagorean identities. So you can look up your Pythagorean identity. Cotangent squared of x equals the cosecant squared of x minus 1. So, substituting in for my cotangent squared, I would have the cosecant squared of x minus 1 minus the cosecant of x equals 1. So, cosecant squared of x minus 1 minus the cosecant of x, that would be minus 1 when I move that over. So cosecant squared of x minus cosecant of x minus 2 equals 0. Factoring, cosecant of x, cosecant of x, and cosecant of x is cosecant squared. I've got a plus and a minus. Since I have a minus on the end, I want a minus in the middle, so minus 2 and plus 1 equals 0. So cosecant of x would equal negative 1, or cosecant of x would equal positive 2. So looking those up, cosecant of x equaling negative 1. Only one I find is 3 pi over 2. Cosecant of x equaling a positive 2 pi over 3. Cosecant of x equals positive 2. Oops. That was under secant. Let's try that again. Cosecant. Under cosecant of x equals positive 2, I'm at pi over 6 or 5 pi over 6. And again, those aren't 180 degrees apart. So I'm going to have 3 pi over 2 plus 2k pi, with k being an element of z. Or I'm going to have pi over 6 plus 2k pi, with k being an element of z. Or I'm going to have 5 pi over 6 plus 2k pi, with k being an element of z. And those would go in for my answer.